SBO is the best.
Okay, let's lock in. This is actually one of the most exam-friendly topics in this whole OCR A-level course because once you understand it, you can explain performance in basically any sport. So the big idea here is that muscles only move when they get energy, and the immediate source of energy your body uses is ATP. So in this video, we're going to break down what we mean by ATP and how it works as the energy currency in the body, what we mean by coupled reactions. We're going to explore the three energy systems: the ATP PC system, the glycolytic system, and the aerobic system, looking at what fuel they use, where they are located, the controlling enzyme that they have, ATP yield, and byproducts. Then we're going to wrap up by looking at the energy continuum and what we mean by epoch. Okay, let's get started with ATP. So what is ATP? ATP actually stands for adenosine triphosphate. And like we mentioned, it is the immediate energy source that your body uses to release energy. So think of it like a charged battery in your muscle cells. When your body needs energy quickly, ATP gets broken down into ADP and P, and that reaction leads to energy being released for your muscles. ADP stands for adenosine diphosphate, and the P is a phosphate, sometimes written as PI because it's an inorganic phosphate. And when this happens, this ATP has been used up, so we need more ATP to continue releasing energy. And the issue is your body actually stores very little amounts of ATP, right? It runs out fast. So we need to turn this ADP back into P to be able to break it down again and release energy again. And this process of topping up ATP is known as ATP resynthesis. And how do we actually perform ATP resynthesis? Is by adding a phosphate to this ADP to be able to convert it back to ATP. So that is what we mean by ATP resynthesis. Now let's talk about energetically coupled reactions. OCR loves the phrase energetically coupled reactions, and it basically just means that one reaction releases energy, and the energy that it releases is used to drive another reaction that requires energy. So the two parts are ATP breakdown, which is what releases energy. This is the energy giving reaction, and that energy is used during muscle contraction. So the muscle contraction part of this energetically coupled reaction needs energy. So it is the energy requiring reaction. Energy requiring reaction. So these are coupled reactions. ATP gets breakdown to release energy, and that energy powers contraction. Now, we're going to talk about the three pathways or the three energy systems. And the three energy systems are all about ATP resynthesis. So we've broken down ATP into ADP plus P. We've released energy, good job. But we need to continue doing that because the more you're exercising, the more energy you need. And the three energy systems are the three different pathways, three different ways that ADP can be converted back into ATP. So the first one we're going to look at is the ATP-PC system. Then we're going to look at the glycolytic system and then the aerobic system. And when we're looking at these, always think about this acronym FABLA, which is an acronym for the different factors you need to be considering for each of these energy systems. So you want to be talking about the fuel use, the ATP yield, the byproducts, the location, the enzyme, and the type of reaction. If you can consistently use this structure, FABLA, to be able to analyze, evaluate, and compare between these three energy systems, you always be picking up those top marks. All right, now let's start with the ATP-PC system or the phosphocreatine system. This system is for instant explosive activities. So think things like a maximum jump, a 100-meter sprint, a heavy lift, or a really quick sprint down a football pitch or a basketball pitch to be able to get to a ball or something like that. So let's break down the Fabler. First, we're going to look at the reaction type. The reaction type for ATP-PC system is anaerobic, meaning no oxygen is needed. The fuel it uses is phosphocreatine, which can be denoted as PC. The location is in the sarcoplasm. The controlling enzyme is creatine kinase. The ATP yield is 1 ATP per phosphocreatine, which means for every phosphocreatine molecule that is used in the reaction to resynthesize ADP, there is 1 ATP that is released. And the byproducts are creatine, phosphate, and heat. So nothing that is overly damaging like lactic acid. And the way the system works in effect is that once that ATP reaction happens to break down into ADP and P to be able to release energy, and obviously you have ADP and P left, and we want to convert that to ATP, the PC molecule, the phosphocreatine molecule, lends one of its P. It lends its P and it adds that with ADP. So it lends its P, adds it with ATP, so ADP and P, and that's able to create an ATP again, and the reaction goes on. And the enzyme here, creatine kinase, helps to be able to facilitate that reaction. And because creatine kinase is involved in the ATP-PC system, the actual products of this ADP plus this P from the PC molecule joining together is ATP plus creatine. So it not just creates this ATP, it also creates this creatine right here, which is one of the byproducts like we spoke about. Now let's look at the strengths and weaknesses of the ATP-PC system. So the main ones really are it has the fastest rate of ATP resynthesis, but it depletes quickly. You can also talk about it doesn't create any harmful products, no harmful byproducts. Limitation also very small yield. Yeah, so that's it for the ATP-PC system. And also something to remember about the ATP-PC system is that it lasts for up to 10 seconds. So any activity that lasts for up to 10 seconds will be powered by the ATP-PC system. So first thing at the top of my head is a 100-meter sprint or a shot put or a javelin throw. Those are movements that are very short duration, very explosive, very rapid. Now let's talk about the glycolytic system. So the glycolytic system lasts for anywhere from 10 seconds to 3 minutes, and it powers any sort of short to medium duration activities, which is why 10 seconds to 30 minutes is sort of short to medium duration. Now let's look at the breakdown, the Fabler breakdown. We have the reaction type. It's anaerobic, which means it doesn't require oxygen. The fuel that it uses is glucose or glycogen, which you get from carbohydrates. It's located in the sarcoplasm, which is found in the muscles, and the controlling enzyme is PFK, or if you want to try pronouncing it, phosphofructokinase. And the ATP yield for this is 2 ATP per glucose molecule or 3 ATP molecules per glycogen molecules. And byproducts, we have lactate and hydrogen ions. So one key thing to note is that lactic acid itself, even though you can safely use that and refer to that, lactic acid itself isn't what makes your muscles burn. It's actually the acidity of the blood, and the acidity is dictated by the hydrogen ions and the lactate in the blood. So let's talk about what's happening in the glycolytic system. What happens is that carbohydrates get broken down into glucose or glycogen through a process called glycolysis. So glycolysis, I'm going to write this right here. This process is what breaks down the carbohydrates into glucose or glycogen. And if oxygen can't keep up with the demand during a physical activity, so if you are doing a really high intensity sprint and the activity is so intense, it demands so much oxygen, but you can't supply enough oxygen to keep up with the demand, then lactate gets produced. And the lactate gets produced to allow the glycolysis to continue. And that is where we have lactate plus hydrogen ions sort of building up in the blood, which links to the fatigue and that pain that you feel in your muscles. So that is really what happens in the glycolytic systems. Now, let's look at the strengths and the limitations of the glycolytic system. So the main one's really that it's faster than the aerobic system, obviously not as fast as the ATP PC system, but it can't be sustained for very long due to muscle fatigue. And also we can add it has damaging byproducts. We can add that it has a higher yield than ATP. Higher yield than ATP. So that's the glycolytic system. Now let's look at the aerobic system. The aerobic system is a long duration system. So it powers anything that lasts from 3 minutes up to hours and hours and hours. So think about long distance cycling, marathon, and all of those long duration activities. So let's look at the breakdown. First, let's talk about the reaction type. It's aerobic, which means it uses oxygen. The fuel is carbohydrates and fats. Those are the main fuel that it uses. The location, it happens in the mitochondria. The controlling enzyme is something known as cytochrome C oxidase. So cytochrome C oxidase. And cytochrome C oxidase forms a key part of the electron transport chain where oxygen is being used. We're going to look at the electron transport chain in a bit. And the ATP yield is 38 ATP molecules. 38 ATP molecules is actually the yield for carbohydrates. So we can say 38 ATP per glucose because we get glucose from carbohydrates, or you could also say glycogen there as well. And this is really amazing because that is around the minimum. If you use fat, you can get a lot more ATP yield from the aerobic system. And the byproducts of the aerobic system are carbon dioxide, water, and heat. Okay, so the aerobic system happens in three main stages. We have aerobic glycolysis, and then we have the Krebs cycle, and we also have the electron transport chain. So aerobic glycolysis is where glycogen gets broken down into glucose using an enzyme, and then the Krebs cycle happens in the mitochondria, specifically in what we refer to as the mitochondria matrix, and the electron transport chain happens also in the mitochondria in what we refer to as the mitochondrial crystate. So these are the three stages of the aerobic system. Now let's move on to the strengths and limitations of the aerobic system. So the main ones really is that it has a huge yield, 38 for carbohydrates, and even more when we are using fat. It can power you for a long duration, and also no harmful byproducts. No harmful byproducts. However, it produces energy at a slower rate, unlike the ATP-PC or the glycolytic system, which release energy a lot quicker. Now, it's important to know that even though we have three different energy systems, energy pathways that are specialized for different types of activity, they are always contributing to activity at all times. It's not a question of whether they are contributing, it's a question of the predominant energy system. So you always want to be referring to the predominant energy system. And the way we can visualize this is through something known as the energy continuum. So if I was to draw a graph here to represent the energy continuum, I would draw something like this, where we are showing the time and the percentage contribution, or just the contribution of each energy system. And we can draw the ATP-PC system here like this, and then the glycolytic system here like this, and then the aerobic system here like this. So this is ATP-PC, glycolytic, and aerobic. And what this shows is at what time period these energy systems are predominant. So the ATP-PC system takes charge up until 10 seconds, and then the glycolytic system takes charge from 10 seconds up onto around 3 minutes, and then 3 minutes and upwards we have the aerobic system taking charge. So that is the energy continuum. Anytime you hear of energy continuum, think about this graph. The energy continuum is basically showing us the interplay of different energy systems based on the intensity and duration of exercise. And because of this energy continuum, it's important to understand that different activities, different sports have different phases, right? And we can refer to this as intermittent exercise interplay. So certain sports like football, basketball, tennis, boxing have different phases. They have phases that are really intense, followed by phases that are not so much intense. And these different phases require a predominance of different energy systems. For example, in football, if you watch a lot of footballers, there's phases where they're just walking. So in a walking phase throughout the match, the predominant energy system would be the aerobic system, because walking is low intensity and footballers usually walk most of the time during the match. But then we have phases where they sprint, we have phases where they are pressing the ball or they're passing the ball really quickly and moving really quickly, and that's where we get an increased predominance in the ATP-PC system and the glycolytic system. Obviously, if it's a fitter performer, then they can rely more on the aerobic system at any given pace, and they can also recover faster in between intense bursts because they can resynthesize ATP a lot quicker. And similar thing for basketball, tennis, boxing. In basketball, when the players are moving up and down, they might be using more of the glycolytic energy systems to get up and down the court. But when they're actually dunking and when they are pressing intensely, then you get an increased predominance in the ATP PC system, because think about it, dunking is really intense. You're slamming the ball and you need to jump high and quickly to be able to do that. Similar thing with tennis, when it's a rally where you're going back and forth, the shuffling movement of the feet could be powered predominantly by the glycolytic system. But when it actually comes time to strike the ball, that strike, which only lasts for less than a second, is powered by the ATP PC system predominantly because it's intense. And again, similar thing for boxing. When you are sort of shuffling around the boxing mats and not necessarily trying to hit a heavy punch, you're just feeling out your opponent, or maybe you're trying to block their punches, you predominantly be using the aerobic system. But when it comes time to actually throw a powerful punch, throw an uppercut, throw a hook, then you will most likely be predominantly using the glycolytic system and the ATP PC system to be able to power your movements. Alright, now let's talk about recovery. This is where we are going to talk about epoch. So for this course, whenever you hear recovery, always think about epoch, excess post-exercise oxygen consumption. And epoch is basically the extra oxygen that your body consumes after exercise to return to a resting state. And when we refer to epoch, it's important to know that it's made up of two components: the fast component, which is also sometimes known as the alactacid component, and the slow component, the lactacid. So you need to know what happens in the fast and the slow component. So let's look at that right now. So what happens in the fast component is that oxygen stores found in both the blood and the muscle get replenished. So oxygen stores in the muscle are known as myoglobin, and oxygen stored in the blood is something we've looked at called hemoglobin. If you're not familiar with hemoglobin, watch the previous video where we spoke about the components of blood. Hemoglobin is a component of blood which carries oxygen. So oxygen stores are replenished in the fast component of epoch, and also ATP and PC levels are resynthesized. Next, we have the slow component of epoch, and what happens is that you experience elevated circulation, elevated ventilation, elevated body temperature, and lactic acid gets removed from the body. And obviously, all of these things that happen in the fast and slow components of epoch get amplified if you were working out a lot more intensely. So the higher the intensity of the activity, then the bigger the epoch that is required. Therefore, the longer the recovery time takes. Okay, that's it for this video. Make sure you check out the resources on our website, Super PE Online, to get everything you need to be able to ace your exams. All right, see you in the next video.